Hello, this is our quiz review practice for the upcoming quiz SLT 5 through 8 honors. The first problem has to do with an avocado selected at random, delivered to a food store where the probability that it is ripe is 0.12, and I'm marking that as R for ripe. The probability that it is bruised is 0.054. That's going to be for a bruised avocado. And the probability that it is ripe and bruised, notice the word and, means that that is the intersection of ripe and bruised. That's going to be marked as ripe intersection with bruised. So as I look at 1A1, it asks what is the probability that the randomly chosen avocado is not bruised. So that's the complement of B, or otherwise known as not B. Since I know that the probability that it is bruised is 0.054, then I know that the complement of that is 1 minus that number. So if it's not bruised, then it's the complement of being bruised. You're going to subtract to get 0.946. 1A2, ripe, given that it is bruised. The word given says that it is a conditional probability, ripe, given that it's bruised. So we have our new definition of conditional, our new formula for that. And so to do the conditional probability, it's the intersection of ripe and bruised over the probability of the avocado being bruised. Both of those numbers are given in the paragraph above, so it's 0.019 divided by 0.054 to give me 0.352. Bruised, given that is ripe, is another conditional probability. I'm going to use the same formula, but this time the only thing that changed is the denominator, because I'm not taking the ripe and bruised in the context of the bruised avocados. Now I'm looking at it in the subgroup of ripe avocados. So once again, these probabilities are given in the paragraph above. 0.019 divided by 0.12 is 0.158. Part 1B asks us to compare the probability of bruised given ripe and the probability of it being bruised. When they are asking us to compare these probabilities, they are heading towards part C, which is going to be talking about independence. So when I compare these probabilities, I can see that they are not the same. So what that tells me is being bruised affects whether the avocado is ripe or not, and the avocado being ripe affects whether or not it is bruised. So in answering our independence question next, where it says, are these events independent, we can use the probabilities from B, because we're always comparing the single probability event, in this case probability of being bruised, with the probability of being bruised in the context of only looking at the ripe avocados. Since these probabilities are not the same, then the events bruised and ripe are not independent. Part 2 asks us to fill out a hypothetical 1,000 two-way table. So we're taking all of our probabilities from above, plus ones we haven't calculated yet, and we're completing our table. So basically we are taking all of the probabilities they gave us above, like bruised and ripe being 0.019, and multiplying every one of those probabilities by 1,000. Once we have all of our givens in there, we can calculate all of the other cells in our two-way table.
Watch out, hazard reported ahead.
Using our two-way table, 2A asks find the probability that a randomly selected avocado is bruised given that it is not ripe. It's easy to do with our two-way table. I am only looking at the not ripe column, in which case I'm only looking at the bruised given that it's not ripe. That's going to be 35 over 880 or 0.04. Going back to question 1, there are 2 additional questions added from a previous year's review. The first question, 1D, asks, what is the probability that if I pick 3 avocados, all 3 of them are ripe? Well, since the not ripe is 0.88%, the probability of picking 3 ripe avocados is going to be the multiplication rule. It's the multiplication rule because this is the same thing as saying the probability of ripe intersection with ripe intersection with ripe. Remember, when we use intersection or and, that's our multiplication rule. So I'm going to multiply the 3 probabilities to get 0.002. 1E can be done a number of different ways. The fact that it says at least 1 avocado not ripe is another way of saying this is an or problem. Either 1 avocado is not ripe, or 2 avocados are not ripe, or 3 avocados are not ripe. That's a lot of probabilities to calculate. I would have to do, I think I said about 7 if you do each one individually and then add them up. For example, the probability of being ripe, intersection with the probability of being ripe, and at least 1 has to be not ripe, so then it would be the complement of ripe. But I would have to do this about 7 different times and add up the different probabilities, because or means add. But I can do it a much easier way. Part D says, well, what's the probability of all of the avocados being ripe? Well, that probability does not include at least 1 not ripe avocado. So if I take the whole of the universe, 1, and I subtract out the probability from D, the probability that all 3 of them will be ripe, I have a much easier way of getting the probability of at least one avocado not being ripe, and that would be 0.998, 1 minus 0.002. For number 3, they give me a lot of different probabilities. For this one, I don't think a two-way table or a Venn diagram would help very much. I think it's just better to sort of pay attention to what our given information is and to use our formulas accordingly. So they're giving us the probability that a randomly selected male is 65 and older. The probability that a randomly selected female is 65 or older. And they're asking us to calculate probabilities based on this information. If a male is selected at random and a female is selected at random, so and is intersection. Intersection means the multiplication rule, so it's going to be the probability of female multiplied by the probability of male. Of course, those 2 probabilities are given. You're going to multiply those probabilities to give the probability of the intersection. If 2 males are selected at random, again, this is the multiplication rule because it's the probability of male and male. The probability does not change if you're selecting the whole U.S. population. That's a lot of people. So choosing 1 male that is 65 and older does not affect the probability that the next man would also be 65 or older. And so you're going to multiply the probabilities of being male. You're going to multiply them by each other to get 0.013. If 2 females are selected at random, the probability that neither of them is 65 and older is the probability of not 65 plus intersection with not 65 plus. Remember, I'm doing complements. Well, since the probability of being female is a female over the age of 65 is 0.146, in order to figure out when they are not that age, it's going to be 1 minus 0.146. That gets us our 0.854. The 0.854 is the probability of the female not being 65 or older. Again, multiplication rule, because it's intersection or and, I'm going to multiply my probabilities here. And the approximate answer is 0.729. For number 4, I can understand why that would seem to be a difficult problem to fill in the missing probabilities when you are only given the universe, the not traveled outside the United States, and not an adult. And the only other numbers they are giving us are the 72 and the 78. So what we don't know is, we don't know the adults not traveled outside the United States. We don't know traveled outside the United States but is not an adult. And we don't know the intersection. In this case, from my perspective, doing a two-way table would help. Fill in the probabilities you know. 0.78 for all traveled outside of the United States, 0.72 for all of the adults, and in this case, since they give us the not, always look for the probabilities in the middle that will be the linchpin to finding all of the probabilities in the problem. The rest of the table is addition and subtraction, making it easier to answer part B. Are the events, is an adult, and has traveled outside the United States independent? Well, using our table, we found that the intersection between adult and traveled outside the United States is 61%. The probability of having traveled outside the United States is 0.78%. So the conditional, using our new definition of the intersection over the second event, is not equal to the probability of being an adult. That answer of 0.61 divided by 0.78, that equals 0.78. Not sure if that's right. But either way, the probabilities are not equal, so we are always going to say not independent. I don't know, did I skip number 4? Nope, that was number 4. Number 5. In a particular calendar year, 10% of the registered voters are called for jury duty. In the city, people are selected at random from all the voters, and the same individual cannot be called more than once during a single calendar year. Be careful here. This has nothing to do with our questions below in terms of replacement. Because if you look at the problem in 5B, it says the probability of being called for jury duty for 2 years. I only have to worry about a person not being called twice in 1 year. So that is information you do not need to do the probability problems. The probability that a registered voter is not called is the intersection, is the complement of being called for jury duty. So that's J prime. J prime is found by taking all of the people and subtracting those called for jury duty. That's 0.9 or 90%. In 5B, where it asks what's the probability that a registered voter is called for jury duty 2 times in a row, if your probability of being called for jury duty in each year is 0.1%. That's the intersection. Intersection means add. I'm sorry, intersection means multiply. And so we're going to do 0.1 times 0.1. And that's going to be a 1% chance for being called 2 years in a row for jury duty. Now we're doing a survey based on whether or not you have a school-age child versus whether you support or don't support the tax based on whether you have a school-age child. So I would first pay attention to what our events are. We've got school-age children, and we have tax, which is going to be T. They give us the probability of supporting the tax at 51%. The probability of supporting the tax given that you have school-age children, because it says of those with school-age children. That's the same thing as saying given. Given is a conditional, so 56% is going to be the probability of supporting the tax given that you have a school-age child. And then they also give us the probability of not supporting the tax given that you do not have a school-age child. Again, this is another given. Givens are conditional. So our 45% is probability of supporting the tax given that you don't have a child. So as long as you can understand that these are conditionals and not intersections, it's fairly easy to do 6A and 6B. The probability a person selected supports the school tax, that's directly from the information given in the question, 51%. In fact, for A2, it's the same thing. Person supports the school tax given. Remember, they were only looking at either people who have school-age children or people who don't have school-age children. In this case, they're saying, do they support the tax given they do not have school-age children? Again, that was a probability given in the original problem. For B, it says, are the events independent? Well, we're very fortunate because the questions above have us comparing probability of supporting the tax versus probability of supporting the tax given that I'm only looking at families with no school-age children. So yes, you can always do it the other way, but why not use the information you've already provided in A1 and 2? And so since these are not equal probabilities, the answers to A1 and 2, then they are not independent. In part C, we're again going to use our new definition of conditional. It says the probability of supporting the tax given that you are 65 or older. Since they give us the intersection, 10% of those responding to the survey were both over age 65 and supported the tax, and means intersection. So I've got the intersection of tax and being over 65. That's our numerator. Then it says, what is the probability that the randomly selected person in the survey supported the school tax given that he or she is over 65? Well, I have the probability of being over 65. So our conditional is going to be the intersection over the probability of being over 65, 0.10 over 0.35. Last one is our M&Ms. In our bag of M&Ms, 9 blue, 6 orange, 5 brown, 5 green, 4 red, 3 yellow, for 32 total outcomes. In our 3 questions, they want to know the fact or the probability of all 3 M&Ms being picked being blue. Let us assume that if we pick a blue M&M, we're going to eat a blue M&M. So if we eat the blue M&M, there is no replacement. If there is no replacement, both the numerator and the denominator are going to change. I started with 9 blue M&Ms. By the time I got to the third pick, it's only going to be 7 blue M&Ms left. When I'm talking about the denominator, there were 32 total M&Ms. If I picked the blue one and ate it, now there's 31 M&Ms. And now at the end, I have, for the third pick, 30 M&Ms left, and only 7 possible that could be blue. So this is intersection. All 3 blue mean probability of blue, intersection probability with blue, intersection probability with blue. So I'm going to multiply our probabilities. You can give it as a fraction, or you can give it as a decimal. 7B, the first one selected is blue, the second one selected is orange, and the third one is selected as red. So for our M&Ms, we start off with 9 blue, 6 orange, and 4 that are red. That doesn't change, because when you pick the first M&M, it's blue. So there's only 1 blue M&M gone by the time you get to the second pick, but they're not asking about picking another blue M&M. So there are 6 oranges left. The third pick, there are still 4 red ones left. What changes is the denominator again. After I eat that first M&M, I've only got 31 total M&Ms left. After I eat the second M&M, there are 30. This is again the multiplication rule, because it's the probability of blue, intersection with the probability of orange, intersection with the probability of red. Intersection means and means multiplication. Last one, the first 2 selected are red and the third one is yellow. Only the red changes from the first to the second pick. So I started with 4 red M&Ms, and then by the time I ate that first one, for the second pick, there were only 3 red M&Ms. For our third pick, there are 3 yellows. I didn't eat any yellow M&Ms, so I'm picking with a possibility of 3 yellow M&Ms on the third pick. My denominator again changes. After I eat 1 M&M, I have 31 M&Ms. After I eat the second M&M, I have 30 M&Ms. And then be careful if you are using your answer sheet from the notes or from Google Drive. You need to check it and make sure that this is in fact your probability as a fraction, and this is what it would be as a decimal. Okay, I hope this helped. Have a good day.